Good afternoon, everybody. I want to offer huge thanks to the organisers for asking me to speak and for creating this workshop. I have to say that in 25, 30 years of being an astronomer, I've never had as much fun as I've had with fast radio bursts. The field just advances in real time. But as Bryan said, even when we have no idea what's going on, we can still use fast radio bursts as probes of their surroundings. So there's much more than I could possibly say in 15 minutes. And so I'm just going to focus on my two favorite probes, which are dispersion and Faraday rotation. Jim will tomorrow give a masterclass on scattering and scintillation, and there's already been some talk about gravitational lensing. So I know some people said that they're sort of new to this field. So just to, someone said, what is SM? Dispersion measure is just a count of the number of electrons along the line of sight, which we measure from the differential arrival of different radio waves. And the rotation measure is the count of electrons along line of sight weighted by the line of sight magnetic field, and we measure that from a twisting of the plane of linear polarization along the line of sight. Now, what pulsar astronomers have known about for decades is that you get the RM and the DM pretty easily, and then even better is that you can then divide one by the other, and modulo a constant, which is not that different from one, RM over DM, just gives you the average line of sight magnetic field. So much of what we're known about the fact that our Milky Way is magnetized and what its magnetic field looks like have come from just measuring pulsar RMs and DMs. And so we can play the same game for FRBs. We can measure their RMs and their DMs, and we can learn about the electrons and the magnetic field along the line of sight. So here's a simple situation with a host galaxy, an FRB in a host galaxy, and we detect the radiation at Earth. But the first thing to realize is that these are integrals. And so we pick up the RM and the DM of everything along the line of sight. So we pick up the DM and the RM of whatever's going on in the FRB or very close to it. We get the DM and the RM of the host galaxy, of the intergalactic medium, and then it travels through the Milky Way's halo and then through the disk. And we get all of those reduced, all that wonderful physics just squashed into one RM and one DM. And sometimes, if we're lucky or unlucky, depending on your point of view, we also get some sort of intervening galaxy, and we get an RM and a DM effect from that. And X has beautifully shown the sorts of interesting halo physics that we can do when that actually happens. So I can't cover all the different things today, but I'm going to mainly focus, not exclusively, but I'm going to focus on my favorite topics, which are the intergalactic medium and the halo of our Milky Way. So let's start off with the intergalactic medium. The first thing I thought of when I heard about fast radio bursts was, I bet you these things are polarized, which wasn't an amazingly visionary insight to say that, and it turns out they were. And I thought, oh, amazing. As soon as we get an RM and a DM for them, we can just divide one by the other, and we can measure, for the first time, the magnetic field of the intergalactic medium. We believe that the IGM is magnetized, and it's possibly where all the magnetism in the universe comes from, but we have never definitively, until recently, measured the magnetic field of the intergalactic medium. So this should be really easy. We just get an FRB, we measure its RM and its DM, divide one by the other, and we have a B, and we're done. It turns out that this formula doesn't work for fast radio bursts, and there are two reasons for that. So let me show you how things go wrong. This is a toy simulation of a magnetized universe that I did with Takuya Akahori, where we populate a universe with an evolving IGM magnetic field. But if you average over all the different complicated effects, you get more or less a typical IGM magnetic field of about 15 nanogauss, not changing too much of redshift. So what we can then do is we can sprinkle fast radio bursts throughout the universe in our simulation and measure their RMs and their DMs and apply that simple formula and see if we can recover this. And it turns out that that formula does an absolutely awful job. And there are two reasons for that. One is that there's these redshift effects that pulsar people have never had to worry about before. And there is this secret part of me that just laughs and with joy every time I hear pulsar astronomers now talking about luminosity distances and redshifts. It's like we're finally joining the rest of astronomy. But DMs and RMs get diluted due to the expansion of the universe, and they get diluted by different amounts. So when you divide RM by DM, you are not correcting for the redshifts don't cancel out. What's more, you're not even comparing apples with oranges, because our best understanding is that most of the electrons are in filaments and voids, where the magnetic field is mainly in the intercluster medium. So you're not comparing apples with oranges. So no surprise that you get completely the wrong answer when you divide one by the other. But it turns out that not all is lost. There's actually a simple correction factor simple correction factor that we identified that can get you back to actually measuring the magnetic field in the intergalactic medium. So this is, in our simulation, what you recover when you apply this correction factor. And it's a very simple correction factor. The numerator is 1 plus z, the average 1 plus z of the filaments along the line of sight. And the denominator is the fraction of the dispersion measure, which is in filaments. Now, while it's a difficult measurement to work out exactly what those numbers are for any specific line of sight, in any given cosmological model, you can work out on average what those numbers are as a function of dm. So you don't even have to know the redshift of your FRB, although that makes it easier. If you have an FRB and you have a dm that you think is mainly cosmological, then under your assumed cosmology, you can work out what that correction factor is, and you can work out the magnetic field of the intergalactic medium. So this seems great, and it's actually been put into practice a couple of times. So one burst that we haven't talked too much about is what I call the Ravi-1 burst, because Vikram's published 2 spectacular bursts, but this one, FRB 150807, we don't have a redshift or a host for it, but it seemed to be along a remarkably clean line of sight. There was almost no foreground Milky Way contamination, and so the extragalactic component in the DM is, sorry, that should be per cubic centimeter, 200 parsecs per cubic centimeter. And the RM, once you remove the Milky Way foreground, was basically 0. And so you can just see how low the RM is on this plot. This is all the pulsars in the Milky Way, their RMs versus their DMs, and you can see that this one is sitting way, way down here. So we seem to have found some sort of window, both in the Milky Way and in the intergalactic medium, where there's almost no magnetic field along the line of sight, presumably out to some significant redshift of, maybe point something, 0.1 or 2 or so on. So if you now apply this formula over here, you can constrain the, put an upper limit on the magnetic field of the intergalactic medium, and you get 20 nanogauss, which is pretty consistent with the rough numbers that we estimated here in this simulation. So this is only one sight line, but it demonstrates that, that you can potentially constrain the magnetic field of the intergalactic medium from FRBs, and the numbers are broadly sensible. So this is assuming uniform, but you can incorporate whatever your favorite coherence length is as well, and it's obviously loaded. That's right. That's right. But we do have estimates. We do have estimates of coherence lengths from other measurements, and you can put your favorite coherent number in there. The other thing that we can do with individual fast radio bursts, so this is when you have one fast radio burst, what can you say, is you can, of course, for the repeating ones, look at how what happens as a function of time. And my personal belief is that the DM and RM of repeating FRBs is going to be one of the key diagnostics of figuring out what's going on just in those sources. And so, for example, in this particular model from Ben and Bryan, you expect Faraday rotation from some sort of nebula around the source that will be measurable, and as the source expands, it will vary in some hopefully smooth way as a function of time. So Tony Pirro and I did a calculation for a very simple situation of a supernova remnant expanding around a young neutron star. And what you find is at early times the dispersion measure drops as the ejecta expand, but then as it starts to sweep up appreciable material from its surroundings, at late times the dispersion measure can actually start to increase again. You can also do the same thing for the rotation measure, and although you again have a competition between the expanding ejecta and the swept up material, the rotation measure in this model should always decrease. But the bottom line is that if you see a smoothly changing dispersion measure and rotation measure, then that might argue that you're seeing something in some sort of supernova or nebula, or perhaps in a white dwarf merger, or anything which involves some sort of explosion which is expanding outwards. And if we see this smoothly varying behavior, then that constrains what is the model for the FRB and its environment, and also its age and other properties. We might also see just some randomly varying behavior, as we might be seeing for the first repeater, and that might suggest a turbulent environment that you might find near an AGN. And at AAS, Andy Seymour said that there's even a hint that maybe the DM of the first repeater might even be sinusoidal in the way it's changing. Jason's saying no, but if we ever see such a thing, then maybe that might indicate orbital periods. So that's what all I want to say about individual FRBs. But of course, we're in this exciting new regime now, as Vicky showed, where we have hundreds and hundreds of FRBs. And obviously, that number is just going to keep going up. So we now have this wonderful sky distribution of fast radio bursts, and we also now have these beautiful dispersion measure distributions that are still need to be interpreted with great caution because all sorts of selection effects are folded in here, and we can start to make statements about whether the repeaters and the apparent non-repeaters have the same or different dispersion measures. But the thing I'm most excited about, being a polarization aficionado, is that CHIME now has this baseband system that Daniele and Ryan McKinven and others have developed, and every time we get a reasonably bright burst now, we get all the polarization information as well. We're starting to move into a regime, as ASCAP have also discovered, where every time we see a decent burst, we get its rotation measure as well. So the total number of sources of rotation measures, which until recently was about a dozen, there's probably 20 or 30 unpublished CHIME ones, and there's going to be many, many more. And so I just love this, that you can see this Faraday rotation with your eye. Here's the waterfall plots, but not in Stokes' eye, as we've been showing this whole conference, but in Q and U, and you can just see with your eye. You could measure with a ruler the rotation measure, but I've saved you the trouble and told you what it is. Here's one of them, and you can see its rotation measure is -63, and here's another one with a slightly higher rotation measure. This one has the sad trombone. It's one of the repeaters. And it's -114. So it's just so beautiful to me to be able to see that rotation measure with your eye. So what can we do with dozens or hundreds or even thousands of rotation measures as well as dispersion measures? So firstly, we can do something about our embarrassing knowledge of the galactic foreground. This is the current state of the art of what the dispersion measure sky due to the Milky Way looks like. And this is from the YMW16 paper, and it's based on the dispersion measures of 189 pulsars. So firstly, it's not based on a lot of data. And what's more, the pulsars are inside the galaxy, not at its edge, so you have to interpolate how far out you go. And what's worse, it actually just completely ignores the halo of our galaxy. It just puts it in the too hard basket, but there's a whole bunch of other papers that very nicely talk about how much extra DM outside this model is in the halo and how it might vary as a function of position on the sky. So we need to do better at that. You might say, well, if we can do it for the dispersion measures, why don't we do it for the rotation measures as well? Well, it turns out we don't need to because it's already been done. So here is what the sky looks like when you have 40,000 sources. And that's because there's another source that has rotation measures in the sky, AGN. They don't have dispersion measures, but they have RMs. And so over a period of decades, we have built up a very detailed map of the rotation measure sky. And you can see that there's all sorts of beautiful structure here. And you can imagine that a better data set will show similar structure in dispersion measure. And what's more, the RMs already have that halo component included, and we have used these RMs to constrain the magnetic field of the Milky Way's halo. But now in this era of lots more FRBs, we can really transform, hopefully transform this crummy picture into something that looks a lot more like this. Certainly in the Northern Hemisphere, we're planning to do that with CHIME. My student Amanda Cook is starting to look at this already with the FRBs that we have. The idea being is that the pulsars are all lower limits on the DM of the halo, and the FRBs are all upper limits on the dispersion measure of the halo. So you can statistically produce upper and lower bounds and begin to map out the halo contribution and see if it's very close to zero or if it's significant and how it varies as a function of position. What we'll be able to do once we get a good, proper DM foreground map, well, firstly, every time we find a fast radio burst, we'll be able to calculate immediately what the Milky Way's DM is at that position and what its RM is at that position and take those off. We try and do that now, but it's somewhat crude, but we'll have a very reliable estimate of the non-galactic contribution of the DMs and the RMs. But what I think is even more exciting is that we'll have RMs and a smooth DM map of the whole sky, and we'll have a smooth RM map of the whole sky, so we can divide one by the other, RM over DM, and we now have B parallel over the whole sky. And this is going to be completely game-changing in working out the magnetic field of our galaxy, which is super important for lots of reasons, including like the origin of ultra-high energy cosmic rays and so on. Because at the moment, every model of a 3D model of the magnetic field of our galaxy has to assume an electron density distribution like the one from YMW16 or NE 2001. And inevitably, whatever assumptions you put in, you also get out again. So these models have inconsistencies or degeneracies that probably come from the wrong assumptions in our electron density model. But dividing RM over DM to first order takes out the electron density, and we can actually get a key constraint on the 3D model of the Milky Way. If we now move on to the intergalactic medium, this is all the localizations that I'm aware of. So there were 7 until yesterday that I knew about, and then Ryan dumped a whole bunch more on us. But the wonders of an iPhone and a photograph, I was able to put those on this plot. So this is the non-galactic contribution of DM as a function of redshift for all of the localized FRBs, and I think there's 11 of them on here. And so the first really neat thing you can see is, as was noted by Ryan yesterday, is that the intergalactic medium does have a dispersion measure, which is a bit of a relief. You can see the DMs going up with redshift. But then you can go a little bit further, and there are all these various published models of how the DM should evolve with redshift, and here are some of them. And you can actually say, at least crudely, that some of them don't do so well. So I think this Pohl et al. Model dramatically underestimates the DM along a given sight line. The classic IOCA one sort of assumes a pure hydrogen IgM is probably perhaps a little bit of an overestimate. But these purple and these red ones, the red one is an MHD one from Klaus Dolag, and the purple one is an analytic one from Bing. They don't seem to do too bad a job, especially when you think that, well, if the IgM is smooth, then these should always be lower bounds because the excess DM is going to come from the host. So we do certainly see some evidence that there's some that seem to have a bit of an excess that presumably is clumpy IgM or an excess in the host. We do have the suggestion that these particular models are perhaps broadly consistent with the data if you think the intergalactic medium is smooth. And as this plot fills up with many more objects, we can actually start to use this relation as a nice distance estimator for new FRBs. We can characterize how much has to be in the host, and we can look at contributions from intervening halos and clumping in the intergalactic medium and so on. There's something else really neat that there's something else really neat that we can do, and that's that we can use pairs of fast radio bursts. One of the problems with rotation measures is that they and dispersion measures that they're always an integral along the entire line of sight, so you don't know where the signal is occurring. But if you have two FRBs that are right next to each other on the sky, then everything in front of the first FRB is essentially in common. And so you can look at the difference in RM and the difference in DM, and that just now has an almost in situ measurement, which is just along this much shorter line of sight. And so this is something that Tessa Wernstrom and I did very recently with AGN, and we think we've used it to detect the magnetic field of the intergalactic medium. But again, with FRBs, we can use RM over DM to get a much more robust number. So as we start to build up very large numbers of FRBs, we can start to do local estimates of delta RM over delta DM, and we can get in situ measurements of the line of sight magnetic field. And we can look at how that varies as a function of redshift, as a function of dispersion measure, and as a function of direction. Taking this even further, the biggest question in this game is, where does all the magnetism in the universe actually come from? Is it primordial? Was it there since the beginning? Or was it astrophysical? Was it generated by stars and black holes? Those two models, and we don't know which one is right, predict completely different distributions of the magnetic field of the intergalactic medium. So what Stefan Huckstein has done is created a toy universe where he's put in these two different possible magnetic field origins and then scattered these universes with FRBs. And you expect to see a very different distribution of RM and DM depending on whether the magnetic field is primordial or astrophysical. And what Stefan's shown, and as you can see on the right here, is that even with only 100 fast radio bursts, localized with redshifts at around a redshift of a half, you can actually start to finally answer this age-old question of whether magnetic fields in the universe are primordial or astrophysical. I know I'm running out of time, so I'll just mention this quickly, but this is what the future holds. Start actually doing sort of real extragalactic astrophysics with FRBs. Start doing cross-correlations with large-scale structure and so on. And so the sorts of things you can do either cross-correlating FRBs with themselves or other traces. You can measure the bias of FRBs, that is, how well do they trace the underlying dark matter structure of the universe. You can statistically constrain the redshift distribution, and you can characterize statistically how much of the DMs towards FRBs are from their hosts and so on. We've already been doing that with rotation measures of radio galaxies to try and statistically measure the magnetic field of the intergalactic medium. So this is a cross-correlation of a simulation showing you that if you have enough rotation measures, you see a signal due to the intergalactic medium. But I think a much more exciting frontier, again, is to use this RM over DM quantity, cross-correlate RM over DM with large-scale structure, and I think this will be a much more robust way of detecting magnetic fields in the universe. So to wrap up, the three things I've talked about are individual fast radio bursts, using them as ensembles and the sorts of techniques you want to use in the future. So I've explained to you that if we actually have locations on redshifts, you can actually say a lot. But even when you don't have those things, time variability is a key diagnostic. And at the moment, we're still limited by the degree to which we can move the foreground. Once we have an ensemble of FRBs, hundreds or thousands or tens or thousands of FRBs, well, then we can now completely characterize the dispersion measure foreground, which we can combine with our already very good map of the rotation measure foreground to map out the magnetic field of the Milky Way, to understand the composition structure of the intergalactic medium, and to start looking at the origin of cosmic magnetic fields. Every one of these conferences, we sort of say the tsunami is coming. Well, I think it's safe to say that it's actually here now. And this means that we have to do some work if we want to make use of these data. And I'm sure we'll talk about this more in the discussion session coming up. But I think that our modeling and our simulations and our tools are still pretty behind the curve. I think there are people working on galaxy surveys and cosmology that can teach us a lot about how to do this properly. This RM over DM seems too good to be true, and it probably is. So we need to think a lot more carefully about when to use it and how to use it. And as Vicky and others have cautioned, when you have lots of data, you can quickly go down the wrong path. We really have to work very hard on our selection functions and systematics. Thanks so much.